Hello everyone, today we are talking about average value of a function. We have found average velocities and average accelerations before, so we're just going to kind of build off of that, and we are going to use integrals this time. So not just the old school slope formula, we are also going to be doing some integrals. Up here in the right hand corner, I've got my classic P and then V and then A. As you go down that list, you're taking derivatives. As you go up the list, you are taking integrals. Just gives us a little bit of grounding there. So let's talk about average velocity. A velocity is the derivative or the slope of position. So to find an average velocity, you're going to find two positions and subtract them, find the difference between them. Let's make one of these little guys, one of those fractions with the subtraction on the top and on the bottom. We will do P of B minus P of A. So it like subtracts the Y values of position or the position values, and then we need the times that are associated with them right below. So this is our old school slope formula because velocity is the slope of position. Now, we know, of course, in our hearts that we could flip this backwards. So if we put A here and B here, then on the top, this would be the same thing as P of A minus P of B, right? Those two fractions are completely equal because we flipped both of the columns with each other. Okay, so that was average velocity. We can find average acceleration in a very similar way. So average acceleration would be the slope of velocity. We keep our B minus A, but since acceleration is the slope of velocity, we need the V function to be on top. So this will be V of B minus V of A. And then just for consistency's sake, I'm gonna swap the two columns. V of A minus V of B. Beautiful. Alrighty. So that's what we've done before. We are now going to apply some integrals to this because we know that sometimes a problem will give you a different set of information but expect you to find the same stuff. So we've got P of T, V of T, and A of T. Look at that, classic position, velocity, and acceleration. Those functions are defined for any time t, and we want to write an equivalent expression for each of the following integrals based on the fundamental theorem of calculus, FTC. Good old FTC. All right, fundamental theorem of calculus is the one where we take the integral by doing like, what is the antiderivative of this little guy, and we plug in a b, and then what's the antiderivative function of this, and plug in an a, and we subtract them. Okay, so we are going to just copy down the 1 over b minus a part. Just leave that, 1 over b minus a. Now we get to ignore that, and we're gonna focus on the integral itself. So we're taking the integral of a of t. The integral of a is v, so this will be v of something minus v of something. I wish I had used a bracket instead of a parentheses there. So I'll fix it. There we go. Bracket. All right, since B was on the top, B is gonna be first. Since A was on the bottom, A is second. Okay, this is equivalent to V of B minus V of A all over B minus A. Oh my gosh, guys, isn't that just the exact same thing as this right here? That's the average acceleration. Okay, so this right here found us the top, right? We can just stick this guy on the top of that fraction because it's multiplication. So this got us the change in velocity, and this shows us the change in time in a denominator. Okay. Me personally, I don't memorize that this is the average acceleration, but I guess you could, right? You're finding acceleration over a certain distance, or the sum of your accelerations over a certain distance. So yes, that makes sense. I rewrite my b minus a, and then I figure out using fundamental theorem of calculus what function I'm going to need and subtract, plug in b minus a. And then from that, I'm like, oh yeah, that's the slope of velocity. It's acceleration. So I literally go through this process every single time because I think memorizing formulas isn't that useful, right? Okay, use the stuff you already know and then build upon it. Next one, basically the same thing, right? Copy 1 over b minus a. I'm gonna be smart this time and put my brackets. Velocity has an integral that is position. All right, and then we'll stick that bracket on the top, p of b minus p of a all over b minus a. That is the slope of position, and the slope of position is average velocity. All righty, cool. This means that to find the average value of a function, we can kind of work backwards. The average value of a function would be the slope for that function. So we would need, let's see, if we have average velocity, the top would have to be subtracting the thing that's above it, right? Subtract the thing that's above it, and that's gonna be on the top. That would be like capital F of B minus capital F of A all over B minus A. So we're gonna build this backwards, starting with something like this. This is going to equal the integral of, let's see, capital F is the integral of little f of x dx. A and B go where they belong, B on top, A on the bottom. And then that will take care of the f of B minus f of A, those capital F's. And in the front, I'm going to put 1 over B minus A. So this right here will find us the average value of little f of x. Dx.